So it is actually indeed my great pleasure to introduce today's speaker, Mr. Sagnik Day, whom I know since last 21 years. We first met on an island which is called Corsica in France, in Mediterranean Sea, and spent about 2 weeks together while attending the first solar summer school. Coming back to the introduction to the speaker, Professor Sagnik Day is the Institute Chair Professor at the Center of Atmospheric Sciences, IIT Delhi. He is also the coordinator of Center of Excellence for Research on Clean Air and Associate Faculty of School of Public Policy and Transportation Research and Injury Prevention Center at IIT Delhi. He received his MSc in Applied Geosciences from Jadavpur University and MTech and PhD from IIT Kanpur. He worked as a postdoc fellow at University of Illinois at Urbana-Champaign, USA. His research interests are to understand the air quality, climate change, and health nexus, and also remote sensing of the Earth's climate system. He has published more than 150 peer-reviewed publications in high-impact journals, which with the H index of 48 and citation more than 10,000. He received INSA Young Scientist Medal in 2008, NASI Scopus Young Scientist Award in 2012, Dr. Sudhanshu Kumar Banerjee MOES Outstanding Young Faculty Fellowship for the period 2011 to 2013, Teaching Excellence Award from IIT Delhi in 2016, and Fulbright Nehru Academic and Professional Excellence Fellowship for 2017-18. He is very well known internationally as well as nationally. Why? Because he is international collaborator for NASA Maya satellite mission, Global Burden Disease of Study, and an expert member of WHO Global Platform on Air Quality and Health. He is serving as a deputy editor of NIHAS Journal of Health and Pollution, associate editor of Atmospheric Environment and Helion, and editor of AGU Journal, GeoHealth, Scientific Reports, and Earth System Dynamics. He is a member of Scientific Advisory Committee of ICMR, National Institute of Research in Environmental Health, Bhopal, National Institute of Occupational Health, Ahmedabad, and PHFI, and also a member of Academic Council of Terry School of Advanced Studies. With these few words, I invite Mr. Sagnik for his lecture. Professor Sagnik.
Thank you, Dr. Niraj, for kind words. Let me share my screen. Okay, I hope my screen is visible.
Yes, it is.
Okay, yes. So again, good evening, everyone, for coming, for the interactions. Maybe next 30-35 minutes, I will talk about air pollution in India, mostly in the context of its health impacts. Because the topic is of interdisciplinary nature, and usually in ISTA, most of the members work more on the measurement and modeling side. I thought this will be a good opportunity to connect the dots and see how the measurement and modeling exercises can be useful to further generate evidence and protect health from air pollution. So I thank my collaborators, but most of the results, in fact, all the results that I'm going to show are the works done by my students. So I acknowledge their contributions upfront. I will talk about first the framework, what we call as environmental health pathway. And that framework will tell us how much knowledge we already generated in the Indian context, and what are the major knowledge gaps. And these knowledge gaps, time to time, I will highlight as I move along with the evidence of air pollution impact on health, particularly with the Indian context. And then also I will highlight what are the potential opportunities for collaboration in future. So let me start first with the framework, which looks quite complicated, but I will explain this to you. So when you talk about environmental health, in the context of air pollution, obviously we have the first indicator, that is the sources of air pollutions. Any atmospheric scientist or meteorologist or environmental scientist that deal with this, you have different sources you can think of, like agriculture, transport, household, power, etc. From all of these sources, pollutants are emitted either in particulate matter form or in gaseous form, and then you have in atmosphere chemistry converting some of these precursor gases into secondary particulate. There are other atmospheric chemistry happening, particularly for ozone and other pollutants. And when we measure the concentration of these different pollutants, the concentrations not only are affected by emissions, but they are also strongly affected by weather conditions. And we know that, for example, summer versus winter, that large difference in the pollution level that we observe in any part of the country, it has a lot to do with the fact that in winter we have shallow boundary layer, which traps the pollutant closer to the surface. But that's where actually the domain of atmospheric scientist or atmospheric science or environmental science ends. Now, if you talk in terms of exposure, which is the first step towards health, we are now venturing into the realm of social science. Because when we think exposure, we are exposed always to some level of air pollution, be it outdoor or indoor. And again, in indoor, we can think of different microenvironments, like, when we are home, depending on the conditions, nearby sources and all, the pollution level may be different. Workplace, for students or children, school environment is extremely important. So all of these actually affect our exposure levels, and that makes us vulnerable. But again, when we come from exposure to vulnerability, it is not just the level of exposure that we are talking about, it is also now the socio-demographic conditions. For example, a person is more vulnerable to air pollution if the person is already having some diseases due to, some other risk factors, because that makes the person more vulnerable for air pollution, particularly if the air pollution and the other risk factors, they contribute similar, to a particular, common disease, for example, cardiovascular disease. So when you talk about vulnerability, definitely then the biological factors are important, because the immunity level is very different from person to person. There are many other factors biologically which actually dictate how vulnerable each individual is. There are sociological factors that determines the difference in the exposure and also the vulnerability to air pollution, ecological as well as behavioral aspects. Now, when we talk about vulnerability, most of the evidence that we have today is at population scale. It is very challenging to actually generate evidence at an individual level, particularly the way epidemiological studies have evolved over the last, I would say, 40 to 50 years. Eventually, now, when you think the impact due to this vulnerability, the impact is throughout our life, from the stage of conception all the way down to old age. We always see there are some impacts, and now we have enough evidence to suggest that air pollution has enormous health burden, and that I will demonstrate in my presentations. When we come to impacts, obviously there are different pathways. You have direct pathway, where a lot of studies, they have shown that exposure to air pollution linking to health outcomes, different types of health outcomes, both physical and mental. Although in India, mental health outcomes are very less explored in the context of air pollution and in general climate, but there are now evidences emerging from developed countries on mental health. In India, we have a lot of evidence now for physical health. We also have indirect effects. For example, air pollution impacts our learning ability. And again, there are studies done both in India and abroad. And if the learning ability is negatively affected, then it reduces the child's potential to earn more when the child grows older. And that eventually leads to, poor economic conditions, which again, has a consequence on the overall health. And similarly, you can think of tertiary impacts through incremental change in the behavioral pattern, through social disruptions, isolations, due to not just air pollution, but in general context of the climate. So you can see that this framework is quite complicated. But when we look at this framework, we realize that we have some evidence at some levels, not for all. But what I'm going to demonstrate in the next few minutes is that the evidence that we have for health, particularly in India, is enough to start acting very seriously. Now, let me start first with the first step, as I said, is the exposure assessment. Whenever we talk about health impacts, the first thing we need to know what is the level of exposure an individual is exposed to. Now, the best way to assess exposure is that if a particular individual carries some sort of monitor which measures air pollution, be it particulate matter or any trace gas, that's the best information that we get. Most accurate, because if you carry the sensor always with you, no matter wherever you are in indoor, outdoor, whatever microenvironment, your exposure level is always captured. However, it is unrealistic and not feasible to scale up for a population, because you cannot expect every person to carry sensor always. And as I mentioned, that most of the evidence that we have, particularly in terms of the health data also, it is not for every individual possible. So we have always randomly selected groups or subjects for which the health data is available, and then we need to connect that health information to exposure and some other covariates that I'm going to explain in a minute. So the question is that how do you really, generate evidence at a population scale somewhat reliably when direct measurement is not practically feasible? One obvious option is I can use whatever ground monitors are there as part of our air quality monitoring network. However, in India, we do not have an adequate air quality monitoring network. Most of the cities have either one or two sensors or monitors. Only city like Delhi, where we have multiple monitors, but even in Delhi also we know that there are parts of the city where there is no ground monitoring available. Now, if in a city I have, let's say, one monitor, most of the Indian cities are like that, or maybe maximum 2 or 3 monitors, how much this data is representative? It is very difficult question to answer, because I really do not know how the exposure varies if I move, let's say, 2 kilometers away from that particular ground monitor, unless I generate some sort of spatially continuous data sets. And here actually comes the importance of the satellite data to provide that spatial coverage to understand this question. And our group has been working for the last 2 decades, specializing in developing exposure database for the country using satellites. And once you develop that kind of data set, then we have shown that it is possible to use that data sets for health studies, and not just simple analysis, but I will show that different types of epidemiological studies actually is possible. But before diving into those studies, let me talk very briefly about how we generate exposure information using satellite data. Most of ISTA members are very familiar with aerosol optical depth, which is a columnar quantity, and which actually the satellite usually retrieves. However, you will see often that the satellite has data gap like this, because when you have clouds, most of the passive sensors do not measure aerosol optical depth. You can still use this kind of database to develop annual statistics and then convert AOD to PM 2.5. However, your statistics will be biased, because often this kind of database means you are missing information. So what we have done is that we developed this algorithm for Central Pollution Control Board. So we standardize this for India, where we fill this kind of data gap in AOD using machine learning. But we need to test how good is the AOD data. Now, the challenge is that if the satellite cannot see or measure AOD on cloudy days, the ground-based radiometers also have the same problem if they are passive radiometers. And in India, we have very, very few active lidars, which is not really enough to do any robust evaluation. So what we did is instead that we randomly predicted AOD from the machine learning model for the pixels where we actually have satellite derived AOD, and almost randomly choosing 500,000 data points, we found that predicted AOD versus actual satellite AOD, they are quite comparable, and we feel that the algorithm is quite robust. Once we have some sort of confidence in that gap filling, then again using machine learning model, and again when I say machine learning model, you have to read this paper because it's not just one model, but before arriving at a particular ML model, we did sensitivity studies to find out which is giving the best results and all. And eventually, then you can convert AOD to PM2.5 on a daily scale. And you can see again that the spatial pattern of AOD does not always match with the spatial pattern of PM2.5 because you may have aerosols present aloft, which can contribute to AOD, but then they will not contribute too much to surface PM2.5. So this, when I say PM2.5, I mean at the surface, that level which we breathe in. So once you have this kind of data, then you can generate statistics. And we have the statistics at 1 kilometer by 1 kilometer scale for the last 23 plus years. We compared them against ground measurements whenever available. You can see on daily scale, monthly and annual scale, the performance is quite satisfactory. So the next step is that when you have this kind of data, now in order to calculate exposure, what we need is to overlay this with demographic information. And now, because today's talk, I am focusing more on the health, so I will give some examples that how using this type of data, health effect is estimated. One framework is provided by global burden of disease. And where, based on the cohort studies done worldwide, we call this kind of graphs as integrated exposure response functions. You can see different colors. Sorry, actually, there is no legend, but I will tell you actually that each individual color represents a particular disease. And how are these graphs created? You have different cohort studies done at different parts of the world where you can actually causally say what is the excess risk of mortality from that particular disease. And you can then attribute that to air pollution. And imagine that you have done 10 studies for different exposure range all across the world. And from those 10 studies, then you can develop this kind of mathematical functions by doing a best fit line. And obviously, it varies from disease to disease. So you can see that for some disease, it is more, although all the functions are non-linear, but you can see that for some disease, there is a very sharp increase within the range of exposure that is around 100 microgram per cubic meter. For some disease, it is more flat after some time. So it all depends on what disease we are talking about. And once you have this kind of data in the GBD framework, then the way burden is calculated is that you need to first know for a geographical entity, be it a city, state, country, whatever, what is the population weighted exposure. Now, why we are giving more emphasis on population is that just imagine there are 4 grids where you know what is the concentration level. But we always, instead of taking simple average of 4 grids, we give more weightage to the grids where more people are living. Because we are concerned about health, so we feel that where more people are living, we should give more weightage, particularly in the context of exposure. So when you do this kind of population weighted exposure calculation for a particular geographical entity, and let's say the number is 100 microgram per cubic meter, then for a particular disease, you can just look at a curve, you can see then for 100, what is the relative risk? And let's say for this particular disease, the relative risk is coming around 1.8. It means that with respect to the reference level, which usually is taken as close to 5 microgram per cubic meter, that is the WHO air quality guideline. That means below 5 microgram per cubic meter annual exposure, as of now, there is no evidence of any health risk. Anyone exposed to PM level more than 5 microgram per cubic meter annually has some sort of health risks based on the current knowledge. So once you know the relative risk, then two other parameters are important. One obviously is that how much people or how many people are exposed to certain level of pollutions, which is indicated here by the population. And the third important parameter is the baseline mortality rate. So for example, let's say you're talking about a disease stroke. And if we know what is the relative risk of dying prematurely from stroke that you can attribute to air pollution, we also need to know what is the baseline mortality rate of stroke. And what do we mean by baseline mortality rate is that here we need to know across all different risk factors how many people are affected by stroke. So if you see this side of the equation, this tells us how many people die prematurely of, let's say, stroke due to all possible risk factors. And the right-hand side of this equation tells us how many people's death rather you can attribute to other risk factors than air pollutions. So once you subtract this from the total, you basically are apportioning the burden only to air pollution. So this is how actually in GBD it's calculated. You have to calculate it disease by disease and then you add it up to say this is the total burden. You need to keep in mind that for some diseases, the risk functions, they are age specific, for example, stroke and ischemic heart disease and all, for example, and it means that if you have more aged people, there will be much larger impact. If you look also in this equation, it is very clear that if you have higher population in a particular region, your burden will be high. If your baseline mortality rate is high, your burden will be high. If your exposure is high, your burden will be high. So all three are proportionally, directly proportional to the burden attributable to air pollution. So if you understand now with this, then same framework is applicable and applied globally. India is the fourth country for where state level estimates are available. You can look into GBD India website to get all the data. And these are the results of the burden attributable to ambient air pollution from 2010 to 2019. Blue is for male, red is for female. And just to give you an idea, what is found is that in the last 30 years or so, for ambient PM 2.5 related mortality burden increased by 115%. One thing I must mention here is that these are estimates. This cannot be directly validated because this is the estimates of burden which you are apportioning to air pollution, and similarly you can calculate the burden from a particular disease apportioned to other risk factor like smoking or something else. But indirectly this can be evaluated. Because this is another confusion. Often people say that how do we really know an individual person has died because of air pollution or smoking or something else? The answer is that no, you cannot. Two reasons. One is that air pollution or smoking are not disease. They are risk factors. No person can die because of air pollution or because of smoking. The person can die because of a disease, for example, stroke or lung cancer or something else. The disease can be caused by air pollution. The disease can be caused by smoking. In most cases, all these non-communicable diseases are caused by multiple risk factors. So at individual level, it is not possible to say for this person suffering stroke, you can say this has happened due to air pollution only or due to smoking or due to something else. So what is usually done is that it is done at a population scale, where once you calculate the burden, for example, if I take 2019, the number something comes around roughly 650,000 or 650,000. So if you see the total death, I think I don't recall exactly the number, but in 2019, air pollution attributable burden is, I think, 1/6 or something. So the total death was 6 times or more than this number. And then you are saying that out of this total death, 1/6 is due to air pollution as a risk. And similarly, as I said, you can do a comparative analysis with other risk factors. The other important point is that when you look into this curve, you see that the burden is increasing. But as I mentioned in the previous slide, that the burden depends on all three factors. So it is not just that the burden has gone up in India only because the pollution gets worsened. Yes, pollution has increased, but not to that extent that can explain this large increase in burden. And we did a study a couple of years ago where we segregated these different factors to understand how much each of these factor is responsible for this increased burden. And just to give you an idea, so between 2000 to 2015, the mortality burden attributable to ambient air pollution increased by around 48%. But when we isolated this factor, we noticed that due to exposure increase, the burden only increased by 17%. So why the total burden increased by 48%? You can see that the population increased during this year, during this period, sorry, and also there is a shift of the age structure to the older generations in many states have pulled up the burden. Only good news is that during this time, the baseline mortality of many non-communicable diseases have declined because of better healthcare and all. And this trend continues, which again kind of partially compensated. And this tells us very important point that when you talk in future, how to really reduce air pollution health, all these factors become important. And it is not just only air pollutions. And because population distribution is so important, we did a study where we looked into how, because people migrate from one place to other, whether that has any role in changing the air pollution health burden. So we looked into the data from 2000 to 2011, so that the first decade of this century. And in that first decade, as per the census statistics, 210 million people in India migrated. And there is interstate migration, there is intrastate migration. What I'm only showing here is the one state to another state migration. And you can see that in India, the migration pattern is very interesting. There are few states like Uttar Pradesh, Bihar, and Rajasthan, from where a lot of people migrated to other states. And similarly, there are some states which are at the receiving end, for example, Maharashtra or Delhi, where a lot of people migrated from all around the country. Now, why migration is important? Because you just imagine two states, from one state, a lot of more people migrated out than the people migrated in. It means that there will be a change in the population weighted exposure, the way I explained earlier. So we exactly quantified that, and based on this, we calculated that due to this migration, this is the change in the mortality burden to PM 2.5 during that decade. And you can clearly see some of these states, as I mentioned, like Uttar Pradesh, Bihar, and all, from where a lot more people migrated out, there was a negative change. On the contrary, like Delhi, Haryana, Gujarat, Maharashtra, where more people moved in rather than moved out, you have a positive impact. And this left panel is mainly for morbidity, which is not the death, but just the disease burden. Again, this is an example that socio-demographic conditions are extremely important when you talk about air pollution health burden. To further help the policymakers, what we did is that we take this burden for every state. The numbers are mentioned here. And then it is apportioned into different sources. You have heard the term source apportionment. So it's the same analogy, like only what we are doing is that here we are trying to understand for every state, there is a air pollution health burden. But depending on the contribution of pollution coming from different sources or different parts of the country, how much we can attribute that to a particular state burden. Now, I will explain this. It's a bit crowded, but for every state, there are two panels here. The left panel shows the contribution of different sectors. And you can see that for all state, secondary emission plays a very important role. And we all know that these precursor gases then form secondary PM 2.5. And that is almost, I think that is important in almost every state. And then obviously, depending on the state and nature of the emission sectors, you can see in some waste is important in some state, transport is very important, industry is very important and all. The right panel here is just the geographical distribution of the pollution sources related burden. For example, for every state, what is calculated is that how much contribution is coming from the emission from within the state, which is this color, how much contribution is coming from the neighboring state, which is this color, long distance, outside India, natural. So the natural here and the natural here, they are quite similar. I mean, natural means is basically the dust and other natural aerosols. Again, the point here is that for all states, you can see there is a varying contribution of own state's emission. And for most of the state, you see there is a significant contributions coming from neighboring state or even outside. It means that regional cooperation is extremely important when we talk about clean air. Moving ahead, as I mentioned earlier, that it's not just the exposure. So my student Devojit has done some analysis. The previous one is also his analysis, where he has calculated that, okay, because India has now implemented National Clean Air Program with a target of reducing 40% pollution levels. So what will happen to the burden if the exposure reduces by 40%, that is in 2026, and then beyond NCAP, let's say every state meets interim target 1 of WHO, that is 35 microgram per cubic meter, which is most likely to be the revised national ambient air quality standard for India. And you can see again, with respect to the baseline, there are some states like Goa or Kerala where you can see there is a clear benefit if you reduce pollution in terms of health. However, states like Delhi or, for example, here Uttarakhand and all, we do not see much benefit. In fact, there is hardly any change in the burden. And this is mainly because in these states, even if you are reducing exposure by a large margin, the population growth is expected to overcompensate the benefit of exposure reduction. And in these states, it means that your exposure has to be reduced by a larger margin for any health benefit. And again, this is very important for policy perspective. So I talked about, how in global burden of disease framework things work. However, I must mention that there are certain limitations in this kind of approach to calculate health burden. One limitation is that the risk functions that I talked about, where the toxicity is not considered because there is not enough epidemiological studies to suggest how the risk varies across the composition. And we all know that PM may be composed of different species. Second important point is that health outcomes that we are talking about, they are manifestation of exposure to multiple pollutants. It's not just PM 2.5. And third thing is that many health outcomes for which there is evidence, they are not included in the GBD because there are not enough cohort studies to really develop that kind of integrated exposure response functions. So with this in mind, whenever we learned very important lessons while doing all these studies, that when you talk about health evidence to the policy makers, always indigenous evidence is more acceptable. And this is why our group, in collaboration with many groups across the country and outside, did series of studies to generate this local evidence. And for that, we did time series studies focusing more on the acute exposure. We did cross-sectional studies to establish associations, and now we are also involved in some cohorts, and I will show one example from each of these. Again, while doing these studies, these are the interesting and important questions that we kept in our mind that, for example, as I mentioned, the GBD does not consider toxicity. So we wanted to understand how important is PM composition when we talk about such kind of evidence. And if PM composition is important, we know that PM composition is related to sources. So then can we really use this evidence to prioritize sectoral mitigation? And finally, because we all know that aerosols have strong climate connection, so any air pollution mitigation that we do will have some climate consequence. So I will first start with this time series studies, which is meant for understanding the impact of acute exposure. Acute exposure means if you have sudden increase in pollution level, in short term, is there an impact? Now for this, the kind of data that is easily available is the all-cause non-accidental mortality, which can be found, which can be available from municipalities or from hospitals. For PM10, there are studies in the literature which I compiled here. You can see for different cities, the excess risk of all-cause non-accidental mortality is different for same increase in the pollution level. And now for PM 2.5, there are 3 studies conducted, and most recently now PHFI has published a 10-city study, which just got published today. So I did not include that because my slides were ready before that. So this is the study done by BHU group. I think it was Nidhi's PhD work, if I'm not wrong. And then for Delhi, there are 2 studies. This one is our group study, and this green one is actually the study led by Bhargav. And now he has done another study with data from 10 cities. And essentially, how we really, calculate this risk. So I will give very quick example. So we look into this data, and then we try to understand how much of this can be linked to PM 2.5. But as I mentioned, that PM 2.5 is not the only cause. So you have to consider other risk factors. So in these studies, essentially, like temperature or humidity are considered as other risk factors. Also, there is a natural trend in the health data. So you can use temporal trend as another kind of adjusting covariates. And then you can basically calculate what is the odds of higher odds of all-cause mortality due to the change in PM 2.5 or any other pollutant for that matter. Often in such kind of time series studies, it is found that there is a time lag, because if today pollution picks up, immediately on the same day, it may not be visible in the data. So all over most of these studies, they do sensitivity analysis first to understand what is the time lag. And I'm just showing example from our Delhi study. You can see we looked into different time lag, 1 day, 2 day, 3 day, like this. And we found that for Delhi, at least the duration which we analyzed, we find 6-day lag is giving the best, possible connections. That means if today pollution peaks, after 6 days, we see most impact on the all-cause mortality. And this results is basically for the 6 day, but then you can actually calculate also with different cumulative days. So this is one way to quickly show policymakers that look, clearly there is an evidence, but this is again for the short impact, short rise. When you talk about long-term impacts, then the best way to do is cohort, but cohorts are very, very resource consuming. Before you jump into cohorts, the best way to do generate evidence is doing cross-sectional analysis. But before that, let me bring in the context of time series studies, what is the role of composition? So with collaboration with NPL, who has composition data for Delhi for many years, we did this collaborative study where using the same health data now beyond PM 2.5, what we have looked is that same thing, like what is that excess mortality risk for increase now in different individual pollutant or rather composition level. And you can see here that PM 2.5 is here. For every species, it is segregated by male and female, but you can see here like nitrate, ammonium, sulfate, elemental carbon and all. And the main message here is that yes, the risk actually is different. For example, you have very large risk for this kind of secondary PM particles as well as elemental carbon, much larger than typical crustal elements or dust and other things. How did we get this data? As I said, like we use the measurements done at NPL and then we sort of combine this with information derived from chemical transport model, and not just for Delhi. Using such kind of hybrid approach, we actually generated information of exposure to different species like black carbon, organic, sulfate and all for the entire country. And not just time series studies, but next I will show cross-sectional studies where we use this kind of data. And for cross-sectional studies, we relied on secondary health data. So these are the government health data captured in the surveys. And the way the survey is done is that almost every district of India is chosen. Every district randomly, some clusters are identified. It includes both urban and rural clusters. Within each cluster, again, 100 to 150 households are randomly chosen. But for every household, we know the coordinates, and it is actually reported in the survey. And from every household, then, series of questionnaires are administered, and some of the biomarkers are directly measured. For example, hemoglobin is measured, but blood pressure is measured, and some other biomarkers are also measured. So both from the biomarker and the questionnaires, then a lot of information about health outcomes and other socio-demographic informations are available. And these are all free data, government data, which anyone can use it. So we took advantage of this, and then we tried to understand for multiple health outcomes, what will happen, when we do the analysis with that exposure data that we generated. However, as I mentioned, that we cannot just directly link health outcome with exposure. We need to consider the confounders, which are the factors which influence both the health outcome and exposure. I will just give you a quick example. Smoking is a, simple example, because if you think of smoking, it affects your exposure. At the same time, the smoking also affects any health outcome that you want to link with air pollution. So similarly, in our model, standard epidemiological model used worldwide, there are ways to adjust for these confounders. There is also a concept of effect modification. That means there are certain factors which do not influence both health outcome and exposure, but rather it modifies the effect that we are trying to establish. And usually, depending on the kind of health outcome that you are looking into, whether it's a binary, and by binary, I mean, for example, if you want to say whether a person is anemic or not. So that's a binary variable. You can also do the analysis with the hemoglobin measured in the survey. Then your health outcome is not binary, but it's a kind of continuous variable. So in case of a binary health outcome, you can use logistic regression. And then I'm not going into details into the methodology, but then as I mentioned, that the idea here is to do the analysis, do the statistical modeling to get the influence of air pollutions. But then when you add all these other terms, these are actually the adjustment you are doing for all the covariates. And again, depending on the health outcome and literature review, you need to choose those covariates. Luckily, most of the covariates are available and captured in the family health survey data. And I will show two examples for this. One is the anemia. And the reason anemia, because we know that India has one of the highest prevalence of anemia, particularly for women and child. We did a study earlier with child. Here I'm showing the results of women. And again, you can see that we adjusted for a multiple different confounders, like diet, very important for anemia, you will all agree, body mass index, gender, wealth, and all. And what we eventually found is that for every 10 microgram per cubic meter increase in PM exposure, anemia prevalence, the odds of anemia prevalence actually is much higher. And then if you want to quantify, then you can say that anemia prevalence increases. I just go back and say that the way we assigned exposure is that because for every this cluster, we know the geocodes. So then it is easier to assign exposure for a particular coordinates rather than taking average over a large region. This figure shows effect modification, which I mentioned earlier, and I will just give one example. So because the information is available about the iron intake at individual level, you can see that when you look into the estimates, this is the odds ratio of anemia for every 10 microgram per meter cube increase in PM exposure. Then the population can be segregated into three categories, like those who have iron intake less than 15 milligram, between 15 to 30, more than 30. And if you see these numbers, so by the way, this is the uncertainty range, each error bars. You can see that clearly the air pollution impact on anemia after adjusting everything else is much higher on those who are having lower iron intake. And this is understandable, because if an individual level, a person is consuming more iron, that will have some protective effect on anemia. And similarly, then we looked into education, other socio-demographic information, body mass index, and many other things. We did the analysis also with different compositions, and again, the same results that we got. You can see that the risk is much lower for sea salt or organic carbon, much higher for sulfate and black carbon. Later on, we repeated the analysis with three different child health outcomes. One is the low birth weight. And for low birth weight, again, the exposure window is during the pregnancy, child anemia, and acute respiratory infections. And you can see again, for different species, for all three diseases, you have different association, but a commonality is emerging that across these different health outcomes, what you're finding is that secondary PM2.5 and black carbon are kind of showing higher associations. We cannot explain biologically why this is the case, for which cohorts are required and recommended. But I think this is a good start to pointing out that composition indeed is very important. What we also did in this study is that because we have the information for each individual composition species, if you say that, okay, let us calculate the risk for each individual species and then sort of aggregate them in a cumulative fashion and see what is the total risk for PM2.5. Obviously, you cannot just add it up because different species have different mass fractions. So we have to adjust for the mass fractions. And when we did that, we are surprised to see that the cumulative risk of different components for each of these diseases were much higher than the risk that you get just using the PM mass. And that is what we argued in this paper, saying that cumulative effect of PM is actually larger than effect of PM mass. And it means that if we use PM mass as a surrogate for health impact, probably we are underestimating. We also did some studies where we looked into, okay, let me skip this. Then let me come to cohort, which is the best study design, and we are collaborating with multiple people. In this case, this is the Garbhini cohort led by THSTI. And this is again preliminary results. So the cohorts, basically, they enroll pregnant mothers before 14 weeks of gestation, and then everyone is followed up. There are all other data. And with our exposure data, what we did is that we looked into how the gestational age at delivery changes as a function of exposure. And you can clearly see that this is coming down. It means that if in pregnancy, mothers are exposed to high level of air pollutions, there is a high chance of premature delivery. We also did some sensitivity study using cross-sectional study design, which I explained earlier, to understand which trimester is more risky. And what we are finding is that you can see that, yes, trimester 1 exposure, is showing much higher association. It means that any increase in exposure during the first trimester has larger potential effect on the birth outcomes than the other trimesters. And all this actually, are quite important to consider in the policy. I just want to mention, in the interest of time, that there are lot of studies now from India. If you talk about child health outcomes, there are studies looking into stunting. This is a long time ago we did. Wasting and underweight, one of my students did in her PhD. Anemia, these three I already showed. There are studies linking with some of these health outcomes for household air pollutions, child mortality, pneumonia, cognitive impairment, respiratory morbidity, and many more. So, similarly for adult, you can see there are studies existing for hypertension, cardiovascular health, women anemia, lipid profile, diabetes, mortality, and many more. So you can see that already there are studies from India that have clearly established that almost all parts of our body are affected by air pollution. Now I will switch gear to move away from PM. I already showed enough evidence to convince you that PM is important, but as I mentioned, there are other pollutants. But again, the problem is that for other pollutants, you need exposure. So one of my student has developed a nitrogen dioxide exposure data. This is an important pollutant, you all know. So she looked into the satellite data first to understand the hotspots, and then later she developed a land use regression model to convert the satellite columnar information to surface NO2. So this paper is under review now, evaluated, and this is just the blow up of the 4 major cities. You can see how the NO2 is distributed. And then she did some studies with the acute respiratory infection information from the family health survey. And again, you can see that there is an increased risk of respiratory morbidity due to NO2 also. Again, one of our MTech students in our department developed a formaldehyde database using satellites. And you can see over India, formaldehyde, which is a proxy of volatile organic compounds, have increased in the last 2 decades. And here she basically quantified at state level how much the exposure has increased. And typically the reference level is considered as 0.7 ppb. You can see that most states, people are exposed to formaldehyde concentrations much higher than what is recommended. And then she further calculated what is the potential cancer risk because of this high level of exposure. Most recently, one of my master students, what she did is that she combined PM 2.5, NO2, and we also got ozone information for the entire country, and she combined these 3 to generate air quality index. And you all know that CPCB has launched air quality index several years ago to disseminate information about air quality, but in a sense that air quality index combines multiple pollutants. And again, you can see how air quality index varies spatially and temporally. And then again, she repeated the analysis with anemia. And 2 important points I want to highlight here. If you see the response function here. First is that you know that in AQI, you have these ranges. Less than 100 is usually satisfactory. 100 to 200 is moderately polluted, and like that. You can see that even in the satisfactory range, there is a risk. And number 2 is that within this range of moderately polluted, you see the risk actually increases. And it clearly tells us that, in terms of health, when you say this whole range of 100 to 200 is moderately polluted and you are putting everyone in the same group as vulnerable, it is not actually accurate. And we need to do more before we really come for better policy recommendations, but this is a good start. So I want to just summarize that while doing all these studies, the lessons that we learned is that yes, PM composition matters. And because PM is linked to sources, we can always target those sources from where those pollutants are emitted. And as I mentioned, that cross-sectional and time series studies are good way to generate evidence for the policymakers, convince them, but obviously more cohorts are recommended to understand the biological plausibility. Finally, I want to say that once we have this kind of data, we can then talk about potential health benefits of reducing exposure. And this is just example for anemia. I picked up the disease because then consistently you can understand. Again, based on the relative risk that I explained earlier, one can calculate that, okay, if your exposure reduces by certain margin, how much the disease prevalence will reduce. And here you can see the four figures. The first one is actually that, okay, if everywhere pollution level decreases as per the NCAP mandate, then you can say that average anemia prevalence will come down from 51% to 45%. And these are the district level statistics. Similarly, if every household switches to clean fuel, again, this number will come down to 45%. If everywhere NCAP target is met, as well as every household switches to clean fuel, then you can see double benefit. The number will come down to 39. And you can see that many districts now will have anemia prevalence less than 35, which is our national anemia Mukt Bharat mission target. And obviously, if India can ever meet WHO air quality guideline, there will be much larger benefit. But I will argue in a minute that it is not possible for India to meet WHO air quality guideline. The reason is that there is this study done in US, but it's a global study. It's a modeling study where they have simulated what is the PM level if there is no anthropogenic sources active anywhere in the world. And if you see the model simulations, you see that over India, typical PM varies somewhere between these two color, which is roughly, I would say, 5 to 20, 25. It means that even with every anthropogenic sector off, you are not below 5. And it is not just India. Most of the places, the authors argued that it may not be possible to meet WHO air quality guideline. Because in India, we have always some background dust present. And this brings again the fact that composition becomes very important, because we need to really think about a realistic clean air target for India. There is a new NASA mission, Maya. The satellite will be launched in a couple of years, where not for the entire globe, but for certain parts of the globe, we will be getting hourly speciated PM data for further health studies. But I think already people have realized that we need to move beyond PM mass. And again, I want to mention this fantastic study by the group led by Dr. Vishal Verma, also Dr. Neeraj, and many other ISTA members are also part of this study, where they showed that oxidative potential varies from place to place. And it means that not every particle is equally toxic. And we need to really reconcile this kind of studies with the population-based evidence that we are generating to further take the dialogue forward and eventually identify that, okay, what or how much actually India can really reduce air pollution with the maximum health benefit. And in my opinion, that this is a good start, but going forward in time, whatever information that we are getting from our studies and other studies is that if we can target those fossil fuel generated species which are more toxic based on the oxidative potential, as well as from this health-based evidence that I showed, probably we'll get much larger benefit. In other way, we can say that even if your PM mass does not change or reduce by that much, there will be much larger health benefit. Finally, I want to say that because of the challenge in the exposure, we are now moving to kind of develop a framework for reconstructing personal exposure at a large population scale, where we are trying to rely on these multiple cohorts where individual level exposure is measured. And these are gold standard data. And we are trying to develop some sort of model based on the socio-demographic information and time activity profiles, information about the indoor conditions, outdoor conditions, and all, so that in future, it is easier for the health scientists to use this kind of data for doing more health-based analysis. My last point is that all of this should feed into the policy, where eventually the target is to develop health-based warning system, which currently we do not have. Then we can assess vulnerability at a localized scale, because right now we are talking about general sense populations. But then if I say, okay, a particular group of people, whether they are more vulnerable or less vulnerable. And this is where actually we need to go in future. Then only we can create and implement adaptation strategies. And we need to keep generating evidence to show that any air quality mitigation exercise that we are undertaking is actually giving positive results. I did not discuss this, but it is very important also to keep in mind that there will be climate consequence if you change any aerosol composition, which also needs to be considered. These are my key takeaways. I will stop here. I will leave this and over to Dr. Neeraj.
Thank you. Thank you so much, Dr. Sagnik, for such an interesting talk. And for the question answer session, I would like to invite Dr. Padma. Dr. Padma, can you please take care of question answer session?
Sagnik?
Yes.
Yeah. Thank you so much for a wonderful talk. It's really very informative and very nice talk. So now we'll take up some questions from the audience. There are some questions in the chat. I will read it for you. The first question is from Jayashri. Why does particulate matter have good association with only black carbon, even though black carbon is mostly fine mode aerosol?
No, I'm not very clear about what do you mean by good associations, but what I was showing in the plots is that with the health outcomes that we considered, both for child and adult, we found that when you consider exposure to black carbon, that is actually showing much larger association. It means that per unit change in black carbon is having much larger health impacts compared to per unit change in other species like dust, for example. But depending on place and emission characteristics, yes, black carbon usually is, I would say, 5 to maybe 8-10% of PM mass. It may vary, it may be lower also, it may be higher also, but that's how. And then I can mention, because you raised this point, is that it means if you reduce black carbon, not only there will be health benefit as per these studies, and black carbon definitely has higher toxicity. I think probably Dr. Neeraj can explain better. But also at the same time, because black carbon is absorbing species, so there will be a climate co-benefit. So that is what I was indicating, that when we talk about mitigation policies and all such interconnected things need to be considered.
Okay, so another question from same Jayashri. She is asking, are there high chances for formaldehyde to form secondary organic aerosol?
There may be some impact on the chemistry itself, but I'm not aware if anybody has looked into this. As far as secondary organic aerosol is concerned, again, the studies are suggesting that yes, SOA is extremely toxic. Total organics may not be that toxic, particularly the primary organics are not that toxic, but SOA is extremely toxic. And again, I think more research is required to further quantify and all.
Okay, Dr. Padma, can I also ask one or two questions?
Yeah.
Yeah. Okay.
Yes.
So Sagnik, means few questions I have. So initially you were showing slides where you have shown this health burden of 2.5 in India, and you were showing that for different diseases there were different curves, and as a function of mass concentration, and some were saturating very initially, and some were saturating after high some certain value. So why something is saturating, means say up to 20 microgram per meter cube, it is increasing sharply and then it become flat. So what could the reason for this kind of behavior?
So it is not exactly flat after 20 or 30. I mean, I just carved it out. If you see the entire range all the way up to maybe 1000 microgram, where studies of household air pollution is there. But yes, the slope kind of tend to flattens out at exposure level more than, I think, I would say 80 to 90 microgram. One reason is that the way this integrated response functions are designed is that a lot of studies, cohorts that are conducted in the ambient conditions, they are all in the exposure range of around, I would say 5 to 35 microgram. And after that, there are a lot of gaps.
Yeah.
Then the studies with the household air pollution, usually the exposure starts around 150 or 200. So you can see that there is a big gap between 35 or 40 to all the way up to 150. So you can imagine you have group of points here, group of points there, and then when you try to fit a curve, you basically do this adjustment. And that is why these curves are not constant. Over the years, when new studies are reported, for example, a couple of years ago, there is a Chinese study published where the exposure range was in the range of 60 in late 60s, which slightly modified the curve. Again, for many diseases, there are no studies available for that range where usually we have exposure in India. So there are a lot of uncertainties, and you are correct. The other explanation is that what people are suggesting, it's not flat, but it tend to flatten out after very high exposure, because typically when you are exposed to levels more than, I would say, several hundred microgram per cubic meter, then further increase really does not increase further health risk. So it is still not fully understood why this saturation happens. But unless we really do more cohorts, we cannot answer fully this. But yes, this is the current status.
Okay, okay, thank you. So one more thing is you were talking about many diseases with PM 2.5 mass. For example, you were talking about delivery time is reducing as a function of increase in PM 2.5 mass concentration. So unless we have some kind of mechanism, okay, this is the reason it is decreasing, then it can be two totally independent thing also, right? Means incidentally they are just showing kind of correlation. Unless we show at least some mechanism that okay, this could be the reason. If you are increasing the mass concentration, PM mass concentration, that is why it is decreasing.
So there are some hypotheses provided in many of these studies, but these are, as I said, like hypotheses. For some of the birth outcomes, I think there are cohorts to explain the biological plausibility, what you were talking about, which is mainly via, because when people are exposed to high level of PM, it triggers inflammations, and then, it has all these different biological consequences. I think the birth outcomes are relatively better studied in cohorts, because a lot of cohorts are focusing on mother and child because they are quite vulnerable, although not fully understood, but there are mechanisms. I have actually in my paper, some of our bio colleagues have provided a hypothesis, for example, why higher exposure to PM increases the chance of anemia, right? So when you think actually what is happening, you can read that paper where they have given this hypothesis, but this hypothesis can only be established when you have the right biomarker measured. But for birth outcomes, such kind of studies already exist where it is given that how that inflammation triggers all these things, which eventually lead to stillbirth or preterm birth or something else, low birth weight, for example.
Just one last question. So somewhere you were showing this relative risk, and then you were showing that it is a function of PM 2.5 mass, temperature, humidity. So other I was able to understand, but humidity, how it is the function of humidity? Means humidity should be embedded in the mass concentration actually.
No. So that was not the risk function. That was basically how acute exposure, impact is estimated in time series studies, where you try to understand the effect of PM, but then you adjust for temperature and humidity. So it's a regression equation. It's not a relative risk. It is basically the health outcome itself is a function of PM, but it is also a function of other parameters like temperature, humidity, and many other covariates, not the risk itself.
Okay. Okay, thank you. Dr. Padma.
Yeah, so we have a couple of questions in the chat box. There is one from Ashirvad Mishra. So he wants to know from you, like your suggestion on some tool or model to carry out the air pollution related health analysis.
I think very quickly, please email me or WhatsApp me. I can, because it's not possible to explain now, introduce any new model, but I will be happy to help you definitely in your study.
Okay, so another question from Sushil Kumar. He wants to know what may be the reason for higher concentration of PM during nighttime compared to daytime.
No, nighttime, I think this is mostly the effect of boundary layer shallowing and trapping the pollutants, which is quite well understood.
Okay. And there is a question from Dr. Sarangi. He's asking about can you please enlighten on which kind of particle or chemical is responsible to cause anemia?
No, it is not like this particle is causing anemia, because what I tried to explain is that higher exposure to PM level increases the chances of anemia. And for that, I was explaining to Dr. Neeraj that our bio and nutrition colleagues that provide a hypothesis saying that higher exposure leads to inflammation, which leads to further, changes in our body, which produces more cytokine, and then it reduces our body's ability to absorb iron. And then that actually triggers or accelerates or increases the chances of having anemia. What I was showing with the different species is that these associations that we are getting at population scale, the risk seems to be higher if people or if PM has larger fractions of black carbon or secondary PM. Again, biological pathways needs to be understood, but that is what actually the data initially is suggesting, that secondary particulate matters and black carbon are showing that they have larger impact. And from the oxidative potential studies, whatever I have read, I also found that these are some of the species, including Shoah, they are also coming as quite toxic. So that's why I said that we need to really reconcile these two.
Okay. So one more question from Sunaina. She wants to ask, I wish to ask that you opted for PMF or receptor modeling to carry out source apportionment studies only. Is there anything else?
Oh, no. We did not do any, you know that for PMF or receptor modeling, usually what people do is that they do sampling and then from the chemical composition. So that's the results that I showed was based on reduced complexity model called GAINS, where it is, very quickly you can basically do a series of simulation scenarios. So it's a kind of a modeling similar to chemical transport model, where you can switch off one emission and see that, how much PM changes, so that you can say that, okay, this much contribution is coming from this particular sector. It is not from PMF, but it is from, it is using that kind of model. And again, if you email me, I can give more information.
Okay. And the question from Karan Vohra, what are your thoughts on PM 2.5 exposure to seasonal emissions sources?
No, obviously, I mean, when I talk about exposure, most of the health studies, as I said, like for long term, usually people usually, annual exposure is considered. Now, in a particular place, if you have sudden increase in the pollution level in a particular season, that will pull up the annual exposure. And one can then calculate, if you suppress that seasonal influx, how much benefit you can get. But for health studies, particularly when you're calculating health burden using GBD framework, I have seen people make mistakes of calculating burden based on only 1 month or 1 week of data, saying that, biomass burning is happening, this is the mortality and all. You cannot do that. You need long-term exposure, at least 1 year, for doing that kind of analysis.
Okay. Again, in continuation to that, he wants to know, is it easy to estimate health burden from it? Should we
No, I
consider?
think Karan, exactly. I think I read that question. That's why I started. Yeah. So I think, Karan, this is what I'm saying. You cannot calculate mortality or morbidity burden using GBD framework for few weeks or months. No, it has to be 1 year at least. Short-term time series studies you can definitely do using the method that I explained in that time series studies. For that, again, you have to choose the health outcome. How easy? Obviously, you have to learn the techniques.
Okay. And one, I think it's going on like, yeah, from Dr. Sarangi, he says, and in such anemia disease, the information on source and pathways of chemicals probably vital.
Yes, I agree. That's what I say that
Mm.
that is what the hypothesis the colleagues are giving, and that is what we are recommending ICMR also to undertake cohorts. And I think AIMS Rishikesh has shown some interest. They are doing some studies in that direction.
Okay, I think there are no more questions. Any questions from the participants or yeah, I think there are no more questions. Then I can proceed to vote of thanks. So on behalf of ISTA, I would like to thank Dr. Professor Sagnik Day at IIT from IIT Delhi for delivering a very interesting and in fact very informative talk explaining the health impacts due to air pollution and the way forward using different methods. Very precisely explained. And one important thing he also brought out is the importance of data sets and the data gaps in understanding the various health perspectives, and the data filling techniques is very impressive, and that is highly appreciated. And so on behalf of ISTA, I also would like to thank TESCON India for sponsoring this lecture. And I also thank all the participants for being part of today's lecture and their active interaction with the speaker. So thank you all. Have a
Okay, thank you, Sagnik.
thank you, Sagnik. Yeah.
Thank you.
Thank you, sir.